In this lesson, we are solving logarithmic and exponential equations. The key is we have to know our laws of logarithms, so you might want to get those out and have them in front of you so that you can refer to them as needed. You might even want to make a summary sheet for this unit just to have all those concepts in one spot so that you don't have to keep flipping back and forth in your notes to look for things. So the first example here says solve each equation by writing it in its exponential form. So I've given you the logarithmic form, and we have to be able to convert that into exponential form. Now you'll notice that all of these equations that we have the argument that is the variable. So my argument is x here. By changing that into its exponential form, we have a base of 4. The exponent is the 5, and that's equal to the x. So x is just whatever 4 to the exponent of 5 is equal to, which happens to be 1,024. So x equals 1,024. So that's really all we have to do with these. 3 to the exponent 6 is equal to our x. That's a 6 there. 3 to the exponent 6, put that into your calculator, should be 729. So x is equal to 729. Now with this one, 2 to the exponent of 9 is equal to x plus 3. Now 2 to the exponent of 9 is 512. So 512 is equal to x plus 3, and then we just need to get x by itself by subtracting 3 from both sides, and we get x is equal to 509. Okay, so don't forget that we're actually subtracting 3 from both sides to get there. All right, the next one, we have 5 to the exponent negative 2, so the base to the exponent is equal to my x. My x, if I apply that negative exponent rule, that means we have 1 over 5 squared, or x is equal to 1 over 25. The next one, now there's no base written. You have to remember that when no base is written, the base is a 10. So 10 to the exponent of 3 is equal to x. X will equal 1,000. Okay, so don't forget that that has a base of 10. Our base this time is 1/2, so I'm going to put that in brackets to the exponent negative 3. That would equal x. If I apply the negative exponent rule, that's going to become 2 to the positive 3, which is an 8. Here we have 3 to the 10. Ooh, wait a second. Nope, not yet. Let's erase that. Eraser, there we go. Okay, so actually that would potentially work. So actually, let's try that. 3 to the exponent of 10 should equal our x squared. 3 to the exponent 10 is really big, so then what we have to do is undo that square by square rooting. And then what we get is whatever the square root of 3 to the exponent of 10 would be equal to. Okay, so 3 to the exponent of 10 is equal to 59,049, and that's equal to x, and square root that, we get 243. Okay, so this actually has two answers, the positive 243 and the negative 243. I'm going to show you an alternate solution to that one. We could also apply our negative, or sorry, not our negative exponent rule, our power law of logs, and that too potentially could go down into the front. And then we could divide both sides. So I'm going to do a second solution here. We could write that as 2 times the log. And then what we could do from here is divide both sides by 2, and we get that the log with a base of 3 of x would equal 5. So 3 to the 5 is equal to x. X is equal to 243. Okay, so we just have to keep that in mind. The reason this one doesn't pull out the negative is that, oops, let's undo that, is that when we talked about our restrictions yesterday on our variable, we said that this thing here had to be a greater than or equal to 0 number. So that's why that negative doesn't actually work for that one. Okay, so if I look at part H, I wonder if I can squeeze H down here. I'm going to put H down here. We've got the log of the root x. So log root x, that really is x to the 1/2 equals 3. And then that 1/2 could come down front. So this is a possibility here. And then we could times both sides by 2, and we get the log of x is equal to 6. Okay, so our x will equal 10 to the exponent of 6. Okay, which we could actually calculate. And that's going to give you 1,000,000 there. Okay, 1,000,000 is your answer for that one. You could do it the other way as well and then just square your answers, square both sides, and that should give you the same answer too. All right, when we move into question number 2 here, we've got the log of 125 with a base of x is equal to 3. I'm also going to write this in its exponential form. My base is x, so we're going to have x to the exponent of 3 equals 125. Now this actually reaches back to our last unit. We want to undo the exponent 3 by cube rooting both sides. So my x will be the cube root of 125. X is going to equal 5 there. All right, same with this one. We would have x to the exponent of 5 has to equal 1 over 243. I'm going to fifth root both sides to undo the exponent 5. Fifth rooting the 1 would give you 1 on the top, and then fifth rooting 243 gives you a 3 on the bottom. So x is equal to 1/3 there. All right, part C here, we now have logs on both sides of the equal sign here. And what happens with this, we can't go into exponential form with this because, well, we could, but it gets a little wonky. We would have 5 to the exponent of log 5, 12 will equal x, and then we could use one of our rules, one of the first 4 rules, and figure out that x is equal to 12. But an easier way, remember when we had like 3 to the exponent of x was equal to 3 to the exponent of 5, and we said that the only way those two things can be equal is if x equals the 5. So we had x equals 5 there for that. Well, the same is true for this kind of question here. Did you notice that we have the log of x with a base of 5, and that log of x with a base of 5 has to equal a log of 12 with a base of 5? The only way that these are going to equal each other is if that x is equal to 12. Whoops. So our solution for this is just plain old x equals 12, and we can make it so much simpler than writing it in exponential form. So if I look at this next one, what I'm going to do before I actually set that equal is I'm going to change that using the power law of logs and have the log of x with a base of 3. That's equal to the log of 7 to the negative 1 with a base of 3. Now again, the only way that those will equal is if x is equal to 7 to the negative 1. So x has to be equal to 7 to the negative 1, which means x is equal to 1/7. Okay, similarly this 4 is going to go up here. We're going to get the log of x with a base of 6 would equal the log of 3 to the 4 with a base of 6. So that means then that x has to equal the 3 to the 4. And then if I actually calculate 3 to the 4, we get 81 out of that. Okay, so hopefully that makes sense so far. Now when I look at this next one, I have my log with an x here. I have this extra part here, which I'm going to move over here by adding the log of base 3 of 4. So I'm actually adding log base 3 of 4 to undo it here. So that gives us the log of log base 3 of x being equal to the log of 12 base 3 plus the log base 3 of 4. Now we had a law yesterday or last class, that we could write these as a single logarithm here. That's going to equal the log, and that could be 12 times 4. And 12 times 4 is 48. So that means that x has to equal 48. Okay, so see how the log laws come into play with this one. The next one here, I want to get my x's on one side. So I have one with x's here. I have this with x's. I'm going to subtract, dang it, subtract the log of x plus 3 with a base of 5 from both sides. I don't know what I'm doing. I keep making a mess here. Okay, so that's going to get rid of this one on this side, and it leaves us with, when I'm subtracting those, they can be written as a single logarithm where they're being divided. And that's equal to negative log 5 with a 7. So again, that negative is going to come up here, and that's going to be equals the log base 5 of 7 to the negative 1. So now we've got an equation here where we've got x over x plus 3 is equal to 7 to the negative 1, and 7 to the negative 1 is just 1 over 7. I'm going to multiply both sides by x plus 3. Multiply this side by x plus 3. That undoes it here, leaves us with an x equals x plus 3 over 7. I'm going to multiply both sides by 7. And that's going to undo these 7's here. So now what I have is, goodness, that 7x is equal to x plus 3. I'm going to get my x's on one side, subtract x, subtract x. And there's lots of different ways to do some of these questions. Just because I did one way, it doesn't mean it's the only way to do it. Sometimes you might be able to find a more efficient way. But, you know, that's the beauty of math. Sometimes there's multiple ways to answer a question. All right, so x equals 1/2 there. Try the next one. I'm looking at subtracting these logs. I would be dividing these two arguments to write that as a single logarithm. We're going to have an x plus 5 divided by an x minus 3. Now on the other side, I just have a number. I know that as long as my argument and the base are equivalent, that's just equal to 1. So this is like 2 times the log of 6 base 6. So then I can take that 2 and attach it there to the 6. So we're going to get log base 6 of x plus 5 over x minus 3 being equal to the log of 6 squared. So the only way that these will equal each other is if x plus 5 over x minus 3, can't read my own writing there, equals 6 squared, which is a 36. Multiply both sides by x minus 3, x minus 3, and solve it there like you would any linear equation. Okay, so that is going to reduce. We get x plus 5 minus 3 groups of 36. 6 times 3 is 8. Carry the 1, that's 108 there. And then we could subtract x from both sides. Subtract x from both sides, and I could add 108 to both sides. Add 108. Oops, 08. That's supposed to say 108. Totally doesn't look like 108. Let's fix that up. We were adding that to undo the other side, which was subtract. Okay, so what we're left with here, 108 plus 5 would be 113, and that's equal to 35x. Divide both sides by 35, and we get x is equal to 113 divided by 35.